finished up last time. What did I do with my clicker? Did I do it back there? Oh, right here. All right. So we finished up last time with single samples test, talked about formal assumptions, right? We want to have variables of some outcome that's continuous. Our outcome is categorical. We can't run t-tests on that, right? Independent observations, and then our distribution of sample means. Technically, do we have any assumptions about the observed scores, Evelina?
Do we have any assumptions about the?
About the observed scores, the actual scores that I'm looking at.
Are we assuming that they're going to be normally distributed?
Well, just a general question. Are we concerned technically with the scores that we have in hand that we're eyeballing in terms of their distribution? No, not technically. The assumption of the t-test is the distribution of sample means, right? So even if we have score distributions, I get a histogram that doesn't look incredibly normal, maybe it looks actually really not normal, right? It's really skewed. But I've got a sample of 50 people, right? Am I necessarily worried about that skew? What do you think, Layla?
Sorry, worried about the skew for what?
For a violation of my underlying assumptions. No, right? Because the assumption is the distribution of sample means. And I know distribution of sample means, even in something that's not normally distributed in the population, even if it is skewed, distribution of sample means very going to quickly approach normality, even in a skewed, on a skewed variable, as long as I have reasonable sample sizes. If I got a sample size of 50, that's pretty good. I'm probably not going to have too much of a problem. Now, if it's really bad, or I have major outliers, right, then that's going to start to become problematic, right? Let's say I've got a sample of 20 and I'm measuring something that ranges from 0 to 100, and most of my people are, you know, down in the 10 to 20 range, and then I got like 2 people who are 100. That's probably going to be more problematic, right? Because with that small sample, that outlier is going to drag those out, particularly it's several units beyond anything else in the sample, right? That's going to be much more problematic. And so we can have rules of thumb, but it's going to require you to do this competently, to think about, well, what am I doing? What are the consequences of this? Is this going to be a big impact? Is it not going to be a big impact? And go through and sort of work through some of that based on sort of your knowledge and understanding of your assumptions and what types of things start to screw up your tests. Okay. So for our single sample test, okay, so yep, we're going to go through do that. Single sample test, we went through those, finished up with that last time. In SPSS, from the pull-down menu, you analyze, compare means, one sample test. You have all of that in your handouts. This is going to be your syntax for your single sample test. You're probably not going to memorize this. You're probably just going to paste it in from the pull-down menu because that's a lot of things to remember. Here's your output. We talked about this. We walked through this last time, calculated some effect sizes. We're pretty excited about what we have going on here. Okay. In Stata, if you were to do this, setup is a little bit different. Here, all I need to do is type in t-test caps total equals whatever my reference value is. This gives me my output here. I could also go to statistics. Stata has a pull-down menu. I could do that fairly easily, but it's pretty easy just to hit t-test, double-click that. That drops it down there, equals 24. Ends up being fairly quick. Here, output is going to look a little bit different, but we see 27 observations, mean of the sample is 62, standard error is 2.56. This is all going to be identical to what you found in SPSS. So here's my standard deviation, 95% confidence interval. Amanda, what's this 95? Give me an interpretation of this 95% confidence interval.
95% confidence interval means that 95% of the time the sample that
Yeah.
Oh,
No.
sorry.
So yeah. So again, with these, I don't want you to go.
Yep.
You're on the right track. It wasn't wrong. It's just something that's going to make my eyes go cross if I'm not a statistical
Yep.
expert.
Got
So give it another try.
95% confidence interval means
So based on these data, what's my best guess for the average CAP score for help-seeking individuals with PTSD in Buffalo, New York?
That it's gonna fall between 56 and 67.
Probably, right? My best guess is 62. This is the average that I got, right? This is my point estimate.
But between 56 and 67 would be a viable or a plausible.
Exactly, right? So
Sorry.
we're saying that this somewhere in here is going to be reasonable estimates. If you say, hey, I don't think it's 62, I think it's 57, okay, that's reasonable. It's not as good as a guess as this, but it's still, based on the data that we've collected, something that would be at least consistent. That would be an estimate for the population value that would be consistent with the model that we put together, okay? But again, be careful here, because remember in SPSS, I mean, what is the confidence interval that SPSS gives us?
Isn't it over 99?
Well, I could ask for a 99 if I wanted to. Is it a confidence interval on my point estimate of the mean? No. So if you look at your SPSS output, it's going to give you a confidence interval around the difference between your point estimate of the mean and whatever your reference value is here, 24.7. So just make sure that you understand the confidence bounds. Your margin of error is going to be identical for both of those. You just want to make sure that you know what the confidence interval is talking about. Okay? Yeah?
What's SPSS using as a point estimate?
It's going to take 62 and subtract 24.7. And so it's giving you a confidence interval around sort of the difference between in your point estimate versus whatever the reference value is for the single sample test. So it's a confidence interval around the difference instead of point estimate mean.
Okay.
But that becomes pretty apparent if you look at the interval estimate and see that 62 doesn't fall in there. You just want to make sure that you're paying attention to stuff.
Why does it, which one do you want? Like, which one is more useful?
Doesn't matter,
Okay.
right? Functionally interchange, it depends on how you want to communicate stuff, right? If you want to say, this is the point estimate, so this is my best estimate for this score in the population, this probably makes sense, right? If you want to say, this, I want to say, like, this population is, so the average score in this population of interest is this many points above or below some reference population, then maybe you talk about the difference. Just kind of depends on how you want to present that information. In certain cases, one will make more sense than the other. Okay. So here's your confidence interval, here's your t-test, degrees of freedom, and then here's your two-tailed test right here, so p less than 0.001.
Yeah, is there a way you know of within the coding itself, syntax, to change that?
To change?
To get the point estimate instead of the difference?
I haven't played around with that too much. I mean, here you could very easily do that, right?
Yeah.
You could just take the difference and then take your critical value, multiply it by your standard error, and derive that on your own if you wanted to. I'm sure there probably is a way to do that. I just haven't played around with it yet. Yeah.
What does the exclamation point mean?
Oh, this means this is just a notation for your two-tailed test. This would be a one-tailed test. This is your other one-tailed test. Here's your two-tailed test. So Stata is giving you two-tailed tests and your two-tailed test and both your one directional tests as well. But again, for the most part, this is probably what you're focusing on. Okay. Questions about kind of the setup here? Again, don't expect most people to go through and sort of rush to Stata, but it's something that I've transitioned sort of my lab over to. It's a really kind of slick program. It'll do some things that SPSS won't. And so, but we'll just keep popping that up. I'll give you reference materials, and if you would want to do it or play around with it, you're more than welcome to. Okay. All right. So, if we were going to go through and write up a single sample test for, say, an assignment, right? This might be text for how I would go through and write this up, right? So go through, take a look. Again, I can't emphasize this enough. This is not a template. I don't want you to cut and paste this into your thing and then just change around values and stuff like that. We've had miscommunications on that in the past, and that ends up getting me sort of agitated, and you being confused is why I'm agitated with you. So this is an example of best case scenario, what I might be looking for in terms of packing all this information into a relatively condensed write-up, right? So at the end, I say summarize your findings. This might be what it looked like. We ran a couple of these, right? So Here's our first one comparing against population with no PTSD here with population with PTSD. Here's just maybe a little bit of, you don't have to worry about this. I'm going to have you do this in your, oh well, yeah. So this is just talking about null hypotheses and things like that. So this is just a very comprehensive way of you communicating to me that you know what these numbers mean, you understand how everything puts together, things along those lines. Well, we're going to write this up for a publication. It's going to be much shorter, right? Because we don't have all the space in the world to just yammer on and on about single sample t-tests. This might be an example of what this might look like in terms of notation, how you might write this up for a publication or something along those lines. Okay. All right, but as we're going through this, as you're running these analyses, always, always, always be thinking about credibility, generalizability, and robustness. Based on what I understand, are these reasonable? Is what I've got a reasonable conclusion based on everything that I know, right? If I'm working with trauma survivors and I find that trauma survivors are doing way better than people who aren't help-seeking trauma survivors in terms of symptoms of depression and social support, what should I do? I should say that doesn't make sense, right? I've probably done something correctly. And this can be as easy as reversing your coding. I think 0 means men and 1 means women, but actually I've coded it the other way, so everything's all backwards, right? Before you get too excited about having something that no one else has ever demonstrated before in their life, make sure that you coded things correctly, that everything's going together. And so wanting to pull all these things into your interpretations so that, one, you make sure that you're sort of accurate, that you've done everything correctly, and then also so that you can say something meaningful about whatever it is that you're looking at. Okay. Okay. Questions on single sample t-tests? All right. So this is nice. We've gone through, we've worked through Z's and T's, and what we've been doing to this point is comparing some sample that I've collected that represents population of interest and comparing those data to some reference value, some reference population, right? I'm saying, here's the population of interest. I can't study all of them, but I can get some of them. And what I want to do is I want to compare these folks in this population to see if they're comparable to some reference population, right? And so this is nice, but once again, these Z single sample tests, the Z single sample T, continue to require more information that's generally available in our sort of day-to-day research. What we're often interested in doing is looking at comparing 2 or more samples with unknown, or 2 or more populations with unknown mean, unknown variance, right? In this situation, we're going to our independent sample test, right? I don't have knowledge of population values for either one of it, or actual population values for either one of these populations of interest. What I can do is I can draw samples from both of these populations and compare these and see if I have sufficient evidence to claim that yes, these populations probably have different values on sort of whatever it is of interest that I'm looking at. So, independent sample t-test, looking to detect reliable differences between 2 population means, comparison of 2 means from unknown populations, or the populations are known, just the parameters associated with those populations are unknown. And this makes up really the foundation of like 80% of the group-based analyses that we do in psychology, right? Like the 2 sample t-test is kind of like it's the bread and butter of psychology research, right? We're saying, hey, is the population from which this sample is drawn, the population from this sample is drawn, do we have evidence that these 2 populations are different on some characteristic of interest? This is what we're talking about here, okay? Our null hypotheses. This is set up a little bit different than we might think. In statistical notation, I'm going to say population mean 1 minus population mean 2 is going to equal 0, right? We can say this difference between the population means is 0, scores are likely drawn for populations having equal means, right? Nick, how might you think we would? So this is kind of weird. Why don't we just say mean 1 equals mean 2? Any ideas?
I don't know if it's just because you're actually looking to see if there's a difference between the two. To say they're the same isn't exactly saying what you're looking for.
Yeah. Functionally, it's the same thing, right? It's interchangeable, but from the perspective of what we do in null hypotheses testing, in like 95% of the time, what's our reference value? What's our null value with a hypotheses test? What was it? 0, right? This just sets it up so my reference value is 0, right? Again, anytime you see that something's statistically significant, even if you have no clue on what the test is or sort of anything that's going on in the methods, probably you can pretty safe bet on, so this test is saying that something is not equal to 0, right? Almost always, okay? So same thing, like I have significant skew in my data. What does that mean, Haley?
It's more than 0.
Yeah, my skew value is not 0, right? Is that always relevant? No, right? The assumption of my test isn't that the skew value is 0. I don't care, right? And if I've got a big enough sample, I'm always going to have significant skew. So someone saying you have significant skew means nothing to me in that I don't know anything about your sample size. I don't know anything about the absolute magnitude of that. All the hypotheses test is just telling me is that it's not 0, right? And so again, getting back to the limitations of our hypothesis test, that something is not 0 is not always a useful thing to know, right? So when we set up our null hypotheses for our independent tests, we're going to say population mean 1 minus population mean 2 equals 0. Difference between the two population means is 0. Scores are likely drawn for populations having equal means, right? Our alternative test, for our two-tailed test, non-directional test, we just set that unequal difference in the population mean, some non-zero value. Observed scores are unlikely to have occurred if means of respective populations were equal. This is getting very technical and being very specific to our null hypotheses tests. This isn't how we often state things, but technically this is what we're saying, right? The way that we go through and run these tests, we're saying, assuming that there is no difference, assuming that these populations have equal means, it would be unlikely that we would find a difference of this magnitude or greater based on our statistical tests that we've run. Okay. So again, these are just general statements, but be very careful when I'm asking you to go through and give me a statement of your null hypotheses, that you're working in population values and that you're understanding who your population is and what exactly we're measuring with this stuff. Okay. All right. So again, at the end of the day, what we're doing is we're saying, asking whether the difference in scores between the two samples that we've drawn, is that difference sufficiently large to conclude that they were drawn from populations having different means. Okay. All right. So our independent sample t-test, some assumptions, formal assumptions. This is just building on the single sample test. One, our outcome variable is continuous. Again, if you ever get in a small panic about, oh, what analyses am I going to use for these data? Very first thing you should always do is break down level of measurement. What's the level of measurement of my outcome? What's the level of measurement of my other variables? That's going to start to very quickly push you into what analyses you need to use. If your outcome isn't continuous, or something that we can treat as continuous, t-tests are off the table, okay? We're saying observations in each sample are independent. Again, this is a methods thing. It's usually not a problem if we were separating sort of this group into that group. Where it starts to get complicated is if we start working with nested designs, right? I'm looking at observations within an individual, like a repeated measures type of situation, or I'm looking at interventions within a class, across schools, things along these lines, right? Those start to become nested structure. But for the most part, unless you're getting complex designs, you won't have to worry about that too much. Once again, distribution of sample means for each population is normal, right? Again, observed scores, not the specific focus. Our observed scores can be kind of ugly as long as we have sufficient evidence to assume that the distribution of sample means is going to be normal, given reasonable approximation of normality in our observed data, or large enough sample sizes.
Not just like at one point in time.
Mm-hmm.
Would that be considered continuous?
Mm-hmm.
Can you
Yeah.
give an example of what wouldn't be continuous?
Oh, someone give me an example, it's not a continuous variable.
Gender.
What's that?
Gender.
Gender's not a continuous variable, right? What else? Rankings, first, second, third, right? Technically, our Likert scales continuous measures? No, they're not. They're ordered categorical at best, right? If they've got enough values in there, we treat them as if they were continuous, and we get away with that okay for the most part. But as you start to get into increasingly complex designs where we have methods that specifically address ordered categorical data, or, you know, I've got a 5-point Likert scale, my modeling programs start to fall apart easier with that versus something that's an actual continuous variable.
Okay.
All right, so these are all comfortable, we know what these are, but now with our independent sample t-test, we have a new one, homogeneity of variance. This is just saying that the variance in both populations is equal, okay? So just like the mean, right? Just like when we're looking at mean, we've got mean of sample 1 and mean of sample 2, right? Do I need a hypothesis test to tell me whether mean is sample 1 and mean sample 2 are equal? No, right? I just look at them. Are they the same number? If they're not equal, right? But I'm not interested in the sample means. I'm interested in the population mean, right? Same thing with my variance. I can go through, I say variance of sample 1 is X, variance of sample 2 is Y. They're not going to be identical, right? But what we're interested in is we want to make sure or get a test to see if this is the distribution of population 1 and this is the distribution of population 2. We want to make sure that the variance of these two these two populations is in the same ballpark. Okay, and we have some tests that we can go through to test that. If they don't, right? If these two, if the variance of these two populations is different, that means that our t-statistic that we normally calculate is no longer distributed as a t-statistic. It has some different distribution, right? And what happens when my test statistic doesn't follow the distribution that I want it to follow? John, what do you think?
Say that again, sorry.
So I'm running this test, right? And my test assumes that the variance in the two populations is equal. If it's not, right? If one population, if I say the variability of whatever I'm measuring in men is much greater than the variability in women, right? But I still charge for and run my test that assumes that those two things are the same. All of a sudden, I've got a test statistic that doesn't fall on the t distribution that I expect it to, right? And what happens? Why is that problematic?
I think like how you calculate your test statistic, it's going to be off. So not like underestimate or overestimate.
Exactly, right? Sort of my critical values that I set that should tell me sort of this is associated with 0.05 probability, that's no longer accurate, right? I'm either have a test that's too conservative or a test that's too liberal, right? And so this is again the problem, and this is why we need to go through and check our assumptions, because if we have a violation of our assumptions that's going to impact our inferences, I can say, oh yes, this is a rare event, but it's actually not a rare event because I'm assuming that my test statistic is falling on this distribution, but it's not. It's falling on something else, right? And if I don't know what that test statistic, how that test statistic is distributed, my confidence in my hypotheses tests are all thrown out of whack. Okay? So we'll talk about how we go through and test our homogeneity to variance assumption. When people see kind of what this homogeneity to variance assumption is getting at. Okay. And then our informal assumptions, again, we don't have huge outliers that are going to start dragging things all over the place, our means all over the place. And then equal sample size across groups. Technically, from a mathematical standpoint, we're assuming that group A and group B have the same number of people in them. Is this often how our research works out? No, right? Sometimes, if we're doing good, and this sort of you experimental folks, right? If you're truly randomizing people into conditions, right? You might be off by 1 or 2 people, not a huge deal. For clinical people, if you're wanting to compare a clinical population with a subclinical population, what happens? In a whole bunch of subclinical or non-clinical folks and a very small sample of clinical folks, this starts to wreak havoc on some of our assumptions, right? It doesn't ruin our tests, but it starts to make it much less robust to certain types of violations of homogeneity, variance, and things along these lines, okay? This is where that Bono paper that I'm having you guys read that's assigned in there, talking about under what situations are t-tests robust and when are they not robust. Sample size is sample size and equal sample sizes across groups are one of those things that start to make our tests more vulnerable to certain types of violations. Okay. All right. So formula. Pretty straightforward. We have mean of sample 1 minus mean of sample 2 minus expected value of population 1 under the null minus expected value of population 2 under the null. What does this value equal, given our standard null hypotheses? 0, right? So that cancels itself out, right? So we're just left mean of sample 1 over mean of sample 2 over the standard error of the difference in means. Okay. Now, standard error and the difference in means, we're talking about the expected difference in means across samples, assuming that the null hypothesis is true. Okay?
Sorry, can you repeat that?
Yeah. Expected difference in the mean across samples, assuming that the null hypothesis is true. Okay? So, just like, and again, so we're back to a sampling distribution, but this time we're talking about the sampling distribution of the difference in means, right? So if I have pop 1 and pop 2, and I'm pulling samples of n equals 30 here and n equals 30 here, okay? If I randomly select a sample of 30 from this population and a sample of 30 for this population, I'm going to get you're going to get some number if I take the difference in those those two means, right? I'm going to get some different score, right? Is this the true difference in the population means? What do you think, Kate? No, it's not, right? This difference score is going to have a sampling distribution, right? Over, if I were to take all possible random samples from this population, subtract it from all possible random samples in this population, all possible combinations here, I would end up with a new distribution of difference scores. Right? And the mean of this, just like everything else we've done, distribution of all possible sample differences, or all possible differences that could be pulled from samples 30 of population 1, sample of 30 population 2. If I went through and graphed all those possible differences between those means, I would get a new distribution, and this is going to be the distribution of my difference in sample means, right? And the mean of this distribution is going to equal my population value, just like everything else. So again, it's just the same stuff that we've been doing. This time, our variable of interest is going to be the difference in sample means, okay? And so this distribution is going to have its own variability, right? And this is going to be the standard error, right? And just like any other measure of standard error, we can think about the standard error as the expected difference between any two randomly selected sort of different scores that we could get across replications, right? We can think about this in terms of how far two random samples from those populations, that difference score is going to deviate from the true population difference. Sort of any of those ways, or how much error to expect, sort of how much variation do we expect just based on random sampling, right? And so again, just like before with our t-test, right? We have the difference we observe versus the difference we would expect just due to sampling error. Same thing here. We've got the difference between population 1, population mean 2, based on our samples that we've observed, over the difference that we would expect sort of just based on random sampling variation. Okay. Now, with this, two sources of error with our independent sample test. One, we've got our mean 1 is going to measure our population mean with error, right? Then we've also got mean 2 is going to estimate population mean 2 with some error. So what this does with our paired or our independent sample test, or two sample tests, we've kind of doubled up our opportunities for sort of fuzziness and error. Okay? So as a consequence, our estimation of our standard error of the differences, okay, needs to account for both of these sources of error. Okay? So what we do for our formula, for our standard error for our independent sample tests, okay, is going to be our variance of sample 1 over our sample size for sample 1, plus variability of sample scores in sample 2 over the size of sample 2. Okay. So if we think about this, standard error for our single sample test is our variance over n, right? That's our standard error for our single sample test, right? You guys have been doing that, right? But for our independent sample test, it's going to be variance 1 over sample 1 plus variance 2 over sample 2, right? So essentially, what have we just done to our standard error? We doubled it, right? Because we've got more opportunities for fuzz in these analyses. Okay. So this is our general formula for standard error. People follow me up to this point? All right. So what we want to do, just sort of kind of walk through and help try and cement some of this into your mind, right? So if we say here we have population 1 in the blue, range 25 to 90. So we've got a range of 70 here, okay? Population 2, scores range from 15 to 65, a range of 50, right? In terms of these two populations. So if we ask what's the possible range of any two randomly selected scores from population 1, population 2, if I'm sampling from this, I could get a sample, or I could get an estimate of 95 off of population 1, or I could get anything as low as 25. Those are all valid scores that I could get. They're not going to happen very often, but they're within their scores I could get. Same thing for population 2. I could get a score as low as 15 all the way up to 65, right? So again, if I want to see what's the possible range of two randomly selected scores taken from the two populations, I could get in one extreme from population 1, I could get a score of 95, and 15 from population 2, I get a sort of range of 80, right? If I'm taking a single score from population 1, single score from population 2, I get as much of a difference of 80. On the other end, if I go through and I select a score of, say, a low of 25 from population 1 and a high of 65 from population 2, I can get a difference of negative 40 there in the other direction. Right?
You always do your population 1 minus population 2?
Well, or you can switch it around, it doesn't matter, right? It'll all turn out the same way. But what ends up happening is I could get a maximum possible range of differences between these two of 120, okay? This is much wider than 75 or 50 here, okay? But if I add these two things together, it's equal to the range of differences that I can get here, right? So if we're thinking, if I, by some infinitely small chance, my value is at the extreme of either one of these two distributions, that means the total score, the total difference score that I could get across these two populations is massive, right? If I'm saying what's the difference between, what's the actual difference in the mean of population 1 and population 2, I could get, it's physically possible to get anything, an estimate from anywhere from -40 to 80 points, right? I could come up with any possible answer from population 1 is 80 points larger than population 2, or population 2 is 40 points larger than population 1, right? It's a massive span. As soon as we start to introduce another comparison group in here, it increases our uncertainty by a great amount. And so what ends up happening is our standard error is we're calculating this. And again, our standard error is how much would we expect this difference score to jump around from sample to sample? Well, our actual range is anywhere a matter of 120 points, right? But that's the very extreme. On average, our standard error needs to go through then and take in sampling variability in our estimation of parameters in population 1 and our sampling variability in our estimation of parameters for population 2, adding both of those in so that we can say, okay, if I'm going to take the difference between these two groups, how much will I expect that estimate of the difference to jump around across replications? Okay. So our sampling distribution of the mean, or our sampling distribution of the difference in means is much greater than our variability of the sampling distribution of just one mean. Okay. People seeing where this extra error term comes into our calculation of our standard error? All right. So here we go, right? We've got variance of sample 1 over size of sample 1, variance of sample 2 over size of sample 2. That's our standard error. Cool. We're set, right? We're good to go? Well, maybe not in terms of applied stuff, right? Because we run into this situation with what if our samples are different sizes, right? This happens a lot. In a perfect world, all our samples would be of identical size, but that never happens in real life. How do we go through and address that, right? Well, we could just plug in whatever the sample size here is in, whatever the sample size here is, right? Well, there we go, easy fix. Problem is, let's say I've got one sample of 10 and one sample of 30, right? Kate, which one of those samples is doing a better job of estimating the population parameters of interest?
30.
Yeah, why is that?
It's just larger.
Mm-hmm. It's a better estimator, right? This sample is going to provide a better estimate of that sample, and so we need to do something to take into account the fact that, again, we're assuming based on the test that the population variability is equal across these two, right? But even though we're assuming that the variance of these two populations are going to be equal, are my sample statistics always going to be equal, Nick? No, they're going to be different, right? I'm going to get a variance of 90 over here and a variance of 70 over here. Well, maybe that's just due to variability, but if this one is a sample of 50 and this one is a sample of 10, I don't want to split the difference and call the midpoint sort of my estimate of variability, because this sample is probably much more accurate than this sample, right? I probably want to weight the heavier sample more, right? And so because we're assuming that the variance of our two populations, we're assuming that it's equal, right? That's why we're doing this test. But what we want to do is we don't want that sample with the smaller estimate, even though we're saying that the values are identical in the population, my sample values are going to be different, right? And so if I want to get a good estimate of the population value, what I don't want is that estimate from the smaller sample to have undue influence on sort of my final estimate of that population variance of these two distributions, right? And so what I'm going to do then is I'm going to start to weight my variance estimate. I'm going to create a pooled variance estimate, okay? people understand sort of the issue with the unbalanced designs and sort of why this starts to impact the accuracy of our estimates. We just don't want to call all things equal because I've got a better estimate than the poor estimate if I'm assuming the actual variance, the actual thing that I'm measuring is equal in the populations anyway. Okay. So what we got is a pooled variance. Pooled variance, this is just the weighted average of our sample variances. Know and love this, this formula. You don't have to memorize it, but it's easier if you sort of start to become familiar with this. Again, this is just a weighted estimate. We're taking degrees of freedom from sample 1. So I got sample size 1 minus 1 times my variance estimate of sample 1. We're going to add to that degrees of freedom for sample 2, n minus 1 times my variance estimate for sample 2 over sample 1 plus sample 2 minus 2. Okay? So again, Evelina, what's going to happen to my pooled variance estimate if I have, say, a sample size of 10 and a sample size of 50?
With the pool variance for the sample size that's smaller, it
Yeah.
will minimize any influences that might be some
Yeah.
estimate.
This sample size of 10 is going to have less weight, right? And so if I have in sample 1 of 10, my variance estimate is 20, and so sample size 2 of 50, my variance estimate is 40. Is my pooled variance going to be closer to 40 or 20? Yeah. Yeah, so say sample size 1, sample size 10 has a variance of 20, sample size 2, sample size 50 has a variance of 40. Is my pooled variance going to be closer to 20 or 40? 40, right? Because it's catching more weight, right? And so we're saying, for the purpose of this test, I'm saying variance in these population, the population variance is going to be somewhere closer to 40 than 20, just based on this is a better estimate than this, okay? Because otherwise what happens? What do we know about our estimation of variance in small samples? Is it too big or too small? What do you think, Emilio?
In the smaller sample?
Yeah.
It'd be too small.
It's too small, and can be like that bias gets increasingly large as our sample gets smaller and smaller. If I got a sample size of 10, right, I'm probably getting sort of everybody right there in the middle, and I have no estimators of sort of the ranges, right? I have a sample of 100, I'm getting a much better likelihood of capturing those people on the margins, right? And so what we don't want is our variance estimates from these small samples to start throwing things way out of whack. Or maybe I get a weird sample. I got 10 people and they're all out on the damn margins, right? If I've got a sample that's larger and doing a better job of getting a good beat on that estimate, I want that to be weighted more heavily in terms of coming up for what our best guess is for the variance of those two populations. Okay. So this is the formula for my pooled variance. And so my final formula for my independent sample t-test is going to be mean 1 minus mean 2. This falls out. So I'm going to have my difference in means over the standard error of the difference in means. And my standard error here, I'm going to plug my pooled variance into my variance estimates here. So I'm going to take my mean difference over pooled variance divided by sample size, the size of sample 1 plus pooled variance over the size of sample 2. This is going to give me my test statistic. My degrees of freedom for my independent sample tests are going to be sample size 1 plus sample size 2 minus 2. Okay.
So you're pulling in the pooled ones?
Yep,
For that one.
just dropping
Okay.
in, same thing as we had before.
Yep.
I'm just using, oops. I'm just substituting pooled variance for our sample variance, okay? So this is the final, this is the formula, okay? Angela, and why do we have minus 2 degrees of freedom here? Or sort of minus 2 up for the degrees of freedom for my independent sample test? Because we have 2 samples, right? So we were estimating 2 variances, right? So we've got one value in sample 1, one value in sample 2 that are fixed. So our degrees of freedom change a little bit for our independent sample test. Okay. Just out of curiosity, why is it important to know degrees of freedom of your analyses? So what's the benefit of this? Yeah?
Would it be to find the corresponding
Yeah. If I'm going through, I need to know, because I gotta find what my critical value is, right? So if this is my test statistic, I wanna know what my critical value is and things like that. What about in reporting, right? What about in, like I'm reading through a paper, why might it be useful to know degrees of freedom and have that reported in a publication? Couple things. Yeah, John.
It could tell you the sample size used for the
Yeah,
test statistic.
Sometimes we get a little fuzzy on who's in what group, right? Well, I go, we've got 7 different analyses, but based on missing data, people in this all our people in this test might not all be on this test, right? If I start getting degrees of freedom associated with those individual tests, it tells me immediately what my sample size is. And if I know what the sample size is, I can tell what the degrees of freedom should be, and if those two things don't match up, I can start to get red flags and be like, oh, wait a minute here, what's going on, right? Other thing too, if I've got degrees of freedom, I can go through and back calculate different types of things, effect sizes and things along those lines. It allows me to go through and start to do some CSI type stuff, going through and sort of figuring out what's going into the calculation of these statistics, be able to start deriving my own stuff based on sort of information provided. You didn't give me an effect size, but I can go through, if I know degrees of freedom, your test statistics, things along these lines, I can go through and reverse engineer quite a bit off of this, okay? So when you're going through and taking a look, writing up your own stuff, thinking about evaluating other research, sort of paying attention to that, because that can help give you additional information. All right, effect sizes, right? Effect size was pretty straightforward and standard for my single sample test, right? Kate, how did we calculate the effect size for our single sample test? You remember?
Wasn't it just that?
I'm just going Z, pretty straightforward, right? I'm just taking the mean of my sample minus the reference point, dividing my sample standard deviation, and that gives me an effect size, right? Laura, how do I interpret that effect size for my single sample test?
Single samples?
What's that? For single sample, yeah.
samples? It's the amount of difference between
In what units?
standard deviation.
Yeah, it's just a Z-score essentially, right? I'm saying that my, sort of based on the data we've collected, my samples falling 0.6 of a standard deviation above the reference value expected in the population, right? Something along those lines, okay? Sample or effect sizes for single sample tests pretty straightforward because we only have one difference, right? And we all have one variance estimate, right? So this ends up being pretty straightforward, okay? We can also use the raw difference too. When we get into our single sample or our independent sample test, things start to get a little bit more complicated, right? We can use the raw difference between sample 1 and sample 2 as our measure of our effect size, right? And this can be useful. Again, if we're using, measuring something that has meaning to people, right? So things like weight loss or income or number of houses or something like that, right? I know what, on average, the difference between 2 houses and 1 house is, right? And I can say, yeah, that's pretty significant indicator of wealth or something along those lines, right? But as we start to work into measures that don't have meaningful units, right? They're arbitrary scales. This raw difference may or may not be helpful, right? If I say my difference is, I'm seeing a difference in neuroticism scores of 15 points, I don't know that that has intrinsic meaning to me because I don't know anything about that scale or what things are scaled on, right? So what we can do is we can start going into, fall back into this, our Cohen's D family of statistics. But what's problematic, Amanda, about just calculating Cohen's D? So I take sample 1, I say take sample 2, and I divide it by the standard deviation. Why is this problematic with our independent sample test?
For independent sample, you have two.
Yeah.
You should have two.
Yeah, I will have 2 standard deviations.
And so you don't have a way to calculate it. Which one do you use?
Yeah, which one do I use, right? Well, I can choose right? But if I'm calculating effect size, which one am I probably tempted to use? The bigger one or the smaller one?
Probably the bigger effect size. Or the one that shows a bigger effect.
That shows
so
you
the
right.
smaller effect size.
Yeah. I'm probably gonna choose, if I've got like one standard deviation is 10 and the other standard deviation is 7,
7.
I'm gonna be tempted to pick 7, right? Because like, oh, well, they're all the same, it doesn't matter, right? And this is, when Cohen came up with this, he said, well, what standard deviation do I use? Cohen would say, well, the assumption is that they're equal in the population anyway, so it doesn't matter. But it actually does matter from a practical standpoint, because what I'm probably gonna do, or at least be tempted to do, is choose the standard deviation that's smaller, that's gonna give me the bigger effect size, and this can start to have quite an impact on our measures of effect. So we've got problems with Cohen's specifying just 1s down here, right? So one of the things we can do is we can calculate, and so as you go through different effect sizes, there's controversy on who gets credit for sort of, oh, this is the thing that I put together, but often Glass is credited with a metric known as Glass's delta, where we take the difference between our two samples and we divide it by the control, okay? Glass's delta is really nice if we have some type of control, okay? So, Amelia, let's say you're doing jury decision research or something like that, right? And you want to say you're rating assumptions of guilt on a 0 to 100 scale, right? And in one jury or one condition, you have people getting standard jury instructions. The other one, you have people getting some sort of modified jury instruction, right? And you find that people getting modified jury instructions are rating people's guilt at higher levels than sort of the control group. Well, in this situation, if I wanted to quantify standardize the magnitude of that effect, I could use Glass's delta, because this is nice, right? I have my control condition. This is the natural state of things, right? This involves like how people generally get things in the general public, right? So we're obviously in our control condition. Not everybody is going to give us the same estimate of guilt, but the variability we see that is, we can assume that that's the variability that we would see in the general population. So Glass's delta is really nice if we've got a study where we've got a strong control group. If we've got a very clear control group, we're saying, all right, based on the variability that we would expect in the general population, we see that people receiving these new jury instructions are rating people's guilt 8/10 of a standard deviation higher than what we would expect just based on sort of natural stuff, right? This is nice, right? So what I've done is I've said, okay, I'm looking at the variability in the control group, and we're saying this is what we would expect just in sort of the way things are right now. So this is a nice standardizer. This is a standardizer that has intrinsic meaning, right? I might not know standard deviation units for what this measure is, but this is just kind of how things exist as they currently are. Same thing like with clinical research, right? If you wanted to say I've got an intervention for depression, let's say I've got an intervention for ADHD, and then I've just got regular medication or something like that. So medication is my control group, and then I've got a new experimental treatment, right? And I go through and I look at the difference between people who've gotten my experimental treatment and people who've gotten just standard medication. Well, I've got a pretty nice established control group here. I might choose Glass's delta because I can talk about the standardized difference between these two groups in the outcome in terms of variability that we would see based on just sort of existing state of affairs. Okay. People understand kind of the intrinsic sort of benefit of Glass's delta. Okay. So this is a nice option, but what happens if we're comparing groups where we don't have a strong control group, right? I want to look at this population and that population. At least I want to look at differences in men and women. Who's my control group? Well, probably not, right? Neither one of them are a control group. Both of them are interest, right? Or I'm running a study where I'm comparing this manipulation versus that manipulation, but they're both things that I'm doing. There's not really a control group in there. Then we start to have problems instituting, sort of collecting a control group because there's not a nice intuitive control group. And so what we can do then is we can, and again, who gets credit for this? but this is often referred to as hedges G. Here we're just using the pool, our standard deviation derived from the pooled estimate. Okay. Don't divide the difference between the two means by your pooled variance. If you do that, Nick, what's going to happen to your effect size?
Your answer effect size is gonna go, it's gonna be small.
Way down, way down, right? But if we've gone through and calculated the pooled variance to run my independent sample test, bless you. What I can do is I can take the square root of that pooled variance, so that's going to give me my pooled standard deviation estimate. Boom, I can use that, right? Again, Evelina, what is my pooled variance estimate?
It's taking into consideration of the size of the samples.
Yeah, right. It's my estimate. It's a weighted estimate of variance across the two groups, right? So if I take the square root of that, then it's just a weighted standard deviation. People in the larger group are going to have more of an influence than people in the smaller group, but this is a nice kind of split the difference effect size, right? Other nice thing about this is the variance estimate, the estimate of variability that's going in the denominator of this is also the estimate of variability that's going into your statistical test. That starts to become important for calculating confidence intervals around your effect sizes. I know what just happened, like inside in your brain, like what, we get to calculate confidence intervals around effect sizes? Yes. Very excited about that. We'll get to that in the next lecture, but yeah.
This may be a really stupid question.
No, it's not. I can already tell.
Can you use an independent samples to test with more than 2 samples?
That starts to become difficult. That's where we get into ANOVA stuff, right? Independent sample t-test is going to be restricted to pairwise tests, right? If we have more, if we want to compare more populations than just 2, we have some different options. This is where we start to get into ANOVA models.
Okay, so then moving back to reserve freedom, that's always going to be -2.
Yep.
We're always gonna have to-
Absolutely. Yep. Okay. All right. People sort of see hedges G here. Okay. And again, talking about sort of interpretation here, right? We're saying sort of using pooled variance estimate as our standardizer, we would expect, half a standard deviation increase in sample A versus sample B, something along those lines. Okay. But one last thing we want to take into consideration is we know that, again, with small samples, we're going to underestimate the variance, right? And if we have underestimated our variance with small samples, what's that going to do to our samples, to our effect size? Laura?
It's going to increase it.
It's going to make it too big, right? And so if I've got sample size 8 and 10, right? Even if I use my pooled variance to weight the 10 bigger than the 8, both of those have probably underestimated the variance in the population. If I've underestimated the variance in the population, that's probably going to mean my effect size is too big. And why am I worked up about the possibility of overestimating my effect sizes, John?
Because you could run into type 1 error.
Well, I've already ran my statistics, right? And so I've already kind of taken a look at that. But just the way our field works, are we concerned that the effect sizes we see in our published literature are overestimates or underestimates of the effect size?
Overestimates.
Overestimates, right? And so now I don't want to contribute even more to that by sort of, I found an effect, right? The difference between my sample of 8 and 10, right? Probably what that means is if you were able to detect that as statistically significant with samples that small, it could mean that the effect that you're looking at is actually really massive, and that's how many people you need in order to detect that. Or it could mean that here's your effect size, but your samples of 8 and 10 just happen to catch something way the hell out here, right? And what we've done is grossly overestimated the actual effect, and so then Nick comes in and tries to replicate with samples 8 and 10 and can't ever do it, and he's mad about the situation. When it really wasn't your fault to begin with, outside of maybe you sort of didn't account for the possibility of your small sample inflating your estimate of effect. And so we have what we call hedges unbiased G. Unbiased G, we're taking our hedges G that we've calculated here, and then just we're incorporating a correction, right? We're gonna multiply our effect size by 1 minus 3 over 4 times sample size 1 plus sample size 2 minus 2, taking that all over the parentheses first, then multiply it before, then minus that by 1. They take all that over, divide 3 by all of that, and then subtract that whole thing by 1. This should give you an effect size that's Haley larger or smaller than G here. Smaller, right? And what we see, if we look at our degrees of freedom, which is corresponding to our samples here, we see that with sample size 2, or you can't do it with sample size 2 because you don't have no variance with, you do samples of 2. But you see, sort of, this is sort of the function of your effect size as your degrees of freedom increase, right? So again, with small samples, we get massive reductions in our effect size, sort of as we go through, once we get to, again, about 30-ish. Again, I can't emphasize enough, don't go around talking about sample sizes of 30 as being large samples. They're objectively not. But if we're looking at standard errors and things like that, we start to see massive reductions in our standard error, or as we start to get up to 30-ish, after that, continuing improvements in standard errors or precision start to go down after that. They still can improve markedly, but so this is kind of what we would expect based on our effect sizes here, right? So anytime you're working with small samples, probably ought to think about, and you're calculating an effect size, probably want to think about calculating unbiased G, or providing a correction to this over this, because this is probably going to increase, right? Now what's going to happen to our correction, Layla, as our sample sizes start to get increasingly large? Yeah, it's going to increase, it's going to correct it less. So if I've got a small sample, the difference between G and G unbiased is probably going to be pretty apparent. If I got really large samples, we're probably not going to get much of a change here. All right. How are people feeling about effect sizes for independent sample tests? I'm going to tell you right now, this is going to be the bane of your existence, because it's going to force you to think about, what am I doing, and then which one of these samples, which one of these effect sizes is going to make the most sense based on what I've done, right? And so when I'm asking you to calculate effect sizes, I'm also going to have you tell me which effect size you're calculating and why. Give me some justification for why you think this is the best measure of effect. This is another reason I think it's hard for people to, why it's taken a long time for effect sizes to catch on in the literature, because it's not an automatic thing, right? Like if I had 7 different t-tests that I could choose from, that would make things difficult, but there's not, there's one, and so I just report that. But if I'm talking about effect sizes, there's a lot of different ways I can go through and calculate this measure of effect, right? And it requires a volitional decision on my part to say, this is the one I want to choose, and this is why, so on and so forth, right? This is a harder thing to grasp for people, and so it's, and our, at least SPSS will not calculate these for you. It requires you to do it on your own. That's an extra step. It's just hurdles that aren't unnecessary or sort of difficult hurdles necessarily, but it's things that keep people from starting to go through and putting this in. But always important, with different number of effect sizes that you could calculate, starts becoming incumbent on you when you're writing things up or publishing papers or for theses, things along those. Be very explicit about how did you calculate your effect size, right? That's an easy thing to put in a footnote. Say, like, I used standardizer, I used pooled variance as my standardizer for between subjects, effects, blah, blah. That's cool. That tells me exactly how you've gone through and done this versus I used Cohen's D. Well, I don't know what that means. That means I think you probably cherry-picked the smaller standard deviation to get the biggest effect sizes, and that's problematic for me, okay? Yeah.
So unless you have a big sample size, would you want to go with, let's say, G instead of like the unbiased G?
Yeah, I mean, I get cell sizes of 20, 30-ish, right? I'll probably go through and just go through hedges G. I mean, honestly, you often don't see people correcting for unbiased G, although you should probably, because this makes my effect size get smaller, and I don't like that. That makes me, and I can get away with just providing this for the most part. If you've got large samples, this is probably going to be fine. You know, if you got cell sizes of 35, I don't think you need to worry about unbiased G. I mean, the correction is going to be relatively small. Again, Hedges G is going to be the default probably in most cases, but also wanting to think about Glasses Delta. If you've got a good baseline, sort of the thing that starts to become important, and the thing that I'm going to want you all to do in this is give me a conceptual interpretation of your effect size, right? We've got small, medium, and large, right? Like we talked about before. But don't just tell me it's a small effect. Tell me what that means, right? I'm going to say sample 2 scores in the second sample were about 0.2 of a standard deviation above those in sample 1, right? Or 1.5 standard deviations above, you got a really big effect size, something like that. Describe that to me in terms of magnitude, not just plugging in a value, because you can calculate a value and have no clue what that means, right? So I want you to incorporate that into your interpretations. Yeah.
Maybe I missed this, but what like determines like if you have like a strong control group? That
That's a conceptual question, right? That's based on, you know, if again, if you were, I can't remember, John, are you more emerging adulthood, ADHD externalizing stuff, or like kid stuff? Emerging adults, right? So maybe we say, here are a group of students with no history of, these are just undergrads with no history of sort of learning difficulties or anything like that, versus my group of individuals, sort of college students with ADHD or on stimulant medications, things along those lines. Well, college students in general with no learning disability, that seems like a nice control group there, right? But let's say we're comparing one group that's getting OT&P versus medication. I don't know that there's a good control. They're both things that are effective. I don't know that one's a good control group, so I might go ahead and just use a G there. Okay.
If you have a sample size that's like 35 or 40, and then your other sample size is like 10, would you use the unbiased to account for that?
Yeah, I might, you know.
I mean, where your sample sizes are kind of very
Yeah.
different.
And so those are the types of things that you're going to want to note in your screening too, that you got very different sample sizes and sort of make some adjustments there.
Okay.
How are we feeling about this? All right. From our secondary analyses, also, I can calculate a between subjects D based on test statistic and samples, right? I can get an estimate of an effect size based on test statistic. I can also take D from 2 times my test statistic divided by degrees of freedom, right? These are ways that I can go through and start to calculate effect sizes based on information that's provided in an article, even if the authors haven't given written an effect size for me, right? They say, oh, well, I've got a statistically significant difference between these groups, and so this means all of these things. I say, well, wait a minute. A pretty massive sample. Let me go through and actually calculate the magnitude of the effect and say, well, your effect is actually quite small, and maybe you should temper your conclusions based on the fact that probably what happens, you were able to detect an effect that we would say is probably reliable, but it's probably more a function of a massive sample size than something that's sort of a huge effect that we want to make a big deal about. All right, so how are we doing? Let's go through, take a break. Take 10, come back, and we'll jump into the example. We'll run through. Again, you're conducting independent. Angela, will you shut that door just so I'm not shouting down the way? You're computing independent samples, t-tests, and running your hypotheses test by hand is probably not something you'll do a lot, but it's a good exercise to make sure that you understand where some of these numbers are coming from. So in this example, we have not a very good study, but it's our study looking at the impact of watching Sesame Street educational programming on later outcome among students. So here we have 10 students who viewed Sesame Street as children compared to 10 students who had not. We looked at mean grade, which on some measure of achievement for each one of these, and saw a difference of 93 for individuals who had watched Sesame Street versus 85 who had not. Okay, so based on the information provided, someone give me the null hypotheses in words. Can you give me the null hypotheses in words here?
The mean grade of children who watched Sesame Street will be equal to 93.
Okay. Close, you're sort of getting there. So can someone jump in and help her out? Okay.
Would it be, the difference in school performance between students who use Sesame Street and those who do not is equal to 0?
Okay, almost perfect. What did Haley miss out there? Yeah, right. So just make sure that let me know when you're writing these down that you know that you're talking about population differences and not sample differences, right? Other than that, you're spot on, right? So we would say our null hypothesis to be tested here is that the population of students, the population of high school students having watched Sesame Street in childhood, their average achievement score will be equal to the population of high school students who had not watched Sesame Street, okay? So just wanted to make sure that you're telling me what it is we're measuring on the outcome, right? And also telling me what our reference population here is, right? Here, we're assuming that we're talking about all high schools, all people who have watched Sesame Street and children versus those who haven't. So we just go through and make an explicit statement there, okay? So we've got our statement of the null hypotheses, null and alternative hypotheses in statistical notation. It's just gonna be this, right? So the mean of the Sesame Street group minus the mean of the non-Sesame Street group is equal to 0. Alternate mean of population Sesame Street minus mean of population not Sesame Street not equal to 0. That's pretty straightforward. Okay.
So in the word one, is it okay to say that one is equal to the other, even though in the mathematical one,
You can
that's
say
not
it.
what we're saying?
Yeah. I'm not gonna. It's functionally the same thing,
Right.
Conceptually, in the conceptual statement, I'm more interested in that making sense to people. So you can talk about the difference. You can talk about them as being equal. You can talk about the difference is equal to 0. However you want to say that.
Okay.
Okay. But formal statistical notation is going to set both of these equal to 0 because 0 is the null hypothesis. 0 is the value that we're testing against. All right. So now what we want to do is calculate a 95% confidence interval for the difference in grades across the samples. Okay. What do I need to do if I want to calculate a 95% confidence interval? What do I need to do first off? Elena? Standard error, absolutely. Okay. So my standard error here is going to be pretty straightforward. Do I have to worry about a pooled standard error here? No, right? I got equal sample sizes, right? So I can say my standard error of mean 1 minus mean 2 is going to be equal to square root of, well, no, so what am I, oh no, I'm good here. 22.2 over 10 plus 17.8 over 10. Okay. Someone tell me what that value is there. What do you got, Laura?
Order same here.
Yeah, same there.
It is gonna be 2, ultimately.
Yeah, that's probably right. I think this is an artificial one. Standard error of 2. Is that correct? Someone else second that for me.
Yes.
Thank you. So I was thinking about this. I was oftentimes I was sort of asking people to calculate things, and we get crickets. We're gonna have this sort of parliamentary procedure. We'll make a motion, like I move the standard error is 2. Maybe someone else to second it, and we'll move on. All right. So we've got a standard error of 2 with this, so we're excited about that. What's the other thing that we need to do? Nick, what else do we need to calculate confidence interval here?
We need a z-value.
Yeah, not a z-value, but our critical value for our t-statistic, right? So in order to get a critical value, what do I need first off to grab that from my t-table? What do we need?
Degrees of freedom.
Degrees of freedom. So how many degrees of freedom for my independent sample t-test here?
18.
18, perfect. 10 plus 10 minus 2, 18 degrees of freedom. So I'm calculating a 95% confidence interval with 18 degrees of freedom. What's my critical value? 2.101. That's what I got. Okay. Perfect. All right. So I've got my standard error. I've got my critical value. I'm ready to rock and roll. Okay. So what's the last thing I need to do if I'm calculating the difference between these two things, Kate?
Sorry, I couldn't read.
Yeah. So I've got my standard error. I've got my critical value. What else do I need for calculating my confidence interval? Point estimate, perfect. And what's my point estimate going to be here? So 93 minus 85?
Oh.
8.
Yeah.
8, right. Okay. So my, here, I'm going to grab a different marker color. So I've got my 95% confidence interval is going to be 8 plus or minus my critical value, 2.101 times my standard error is 2. This is going to give me a confidence interval. On the low end, I'm going to have 3.80. On the high end, 12.20. Okay. I'll pick on someone on this side because I don't know that anybody on that side can actually see what's going on here. Okay. Amanda, can you give me an interpretation of this confidence interval?
That an acceptable difference between, a plausible difference between high school students that watch Sesame Street and high school students that do not watch Sesame Street would fall between 3.8 and 12.2.
Yeah, okay. So again, we're just pulling this in. We're saying based on the data that we've collected, we're finding that high school students who have watched Sesame Street are scoring about 8 points higher on whatever academic achievement measure we've calculated. However, based on the data we've collected, we would say values between 3.8 and 12 point, an increase of 3.8 to 12.2 point difference would be sort of reasonable based on the data. We could say we would expect sort of values falling below 3.8 or above 12.2 are going to be relatively inconsistent with the data that we found. We're going to say we expect a margin of error of about 4.2 plus or minus, right? So we say point estimate of 8 with a margin of error plus or minus 2 points or something along those lines. However, we want to go through and describe that. Okay, Nick, if my confidence interval goes 3.8 to 12.2, I see eventually I'm going to run a hypotheses test. What do I already know about my hypothesis test?
That you would
You're 50%.
I know. I'm trying to figure out how much better than 2 years ago.
Am I going to reject or fail to reject the null hypothesis?
Reject.
Reject, yeah. And how do I know I'm gonna reject?
Because the interval is above their critical value.
Yeah, well, because, not because the interval is above my critical value, it's because my interval doesn't contain the value specified in the null hypothesis, right? If zero difference was included in my interval estimate, I would know that eventually I'm gonna fail to reject the null hypothesis. But if I say that, well, I think actually the population difference in achievement is actually 0, what would you say, Layla, given this confidence interval?
I'm sorry, can you repeat that?
Yeah, what if I say, well, I think the difference between these two populations in achievement is actually 0? What would you say based on the confidence interval we have here?
That we did something wrong because if it's actually 0.
Well, 0 is just a number that I've said, well, I don't think Sesame Street does anything. I think there's 0 difference in academic achievement. Based on the data we've collected, what would you say if this was our confidence interval?
If there actually is a difference.
Right. I'd say, well, I don't know, maybe it is, but 0 is not a plausible value based on the data that we've collected, because these are the range of plausible values. 0 is not in that range, so maybe it is, but based on the data we've collected, we have some level of certainty that it's actually not, the difference in populations is not 0. Okay.
So we're rejecting one because 8 falls within that range?
No,
Nope.
because 0 doesn't.
0 doesn't fall in that range, right? Because 8 has to fall in this. 8 is our point estimate. 8 is our population estimate, right? So if 8 doesn't fall in here, then we've got problems, right? But what we're looking for is whether or not our value specified under the null, right? Value specified under the null is 0, right? The 0 doesn't fall in this, so that we know that we can say with confidence that there's an effect. All right. Next thing we want to do is calculate a index of magnitude of effect. What should we be thinking about in terms of calculating an effect size for these data?
Very small samples.
There's small samples, okay. So we want to pull that into account. Do I have a good control group? Kind of, right? I could make an argument to say the kids who didn't watch Sesame Street are sort of my control group, right? So I could calculate Glass's delta here, but I've got pretty small samples. I might go with an unbiased G, right, with this. And so if I'm going to go through and calculate my effect size here, right, what do I first need to do?
You need to find the pooled variance.
Yeah, I would need to find the pooled variance. Now, here, technically, we don't need to find the pooled variance. We could just take the average of the two variances, because the sample sizes are equal. But we'll just run through pooled variance just as an exercise, okay? So, let me say, I'm going to say my pooled variance is going to be equal to 10 minus 1 times 22.2 plus 10 minus 1 times 17.8. Take all of that over 10 plus 10 minus 2. Okay. So again, with equal sample sizes, we actually don't need to pool. We just calculate sort of the arithmetic average of this and we'll be fine. But just to see how this is going, we've got degrees of freedom for sample 1 times variance of sample 1, degrees of freedom 2, variance of sample 2 over sample size 1 plus sample size 2 minus 2. Yeah.
Is it 22.2?
Yeah. Okay. And so if I calculate this out, I'm going to get a value of 20. That actually turned out to be nice, right? Okay. What do I need to do now to calculate my effect size?
Which one are you using?
I'm going to use my unbiased G.
You have to do your biased G first.
Yeah, you have to calculate G first, right? So I'm going to say,
93 minus 85.
what's that?
So you'll do your M1 minus M2, so 93 minus 85.
Right, so, and we already know that's 8, right? Divided by what? Oh, not 20. Why not 20? It's 20 by variance, right?
You
So we need to take the square root of that, right? So what's the square root of 20?
1.472.
Okay, 4.472, okay? Which gives me an effect size of what? 1.789. Excellent. Okay. So, couple things to note here. Always make sure when you're pooling variance and you're getting this pooled variance estimate for G, make sure you're taking the square root of the pooled variance and not just averaging the standard deviations, okay? The square root of the pooled variance and your pooled standard deviation, those are going to be different things, okay? They're not mathematically equal, right? So with this stuff, anytime you're using something based on a pooled variance estimate or a pooled standard deviation, make sure that you're pooling the variance first and then taking the square root of the pooled variance, because if you just average if you take this, in this case, if we take the average of the variances and square it, and if we were to take the two standard deviations and take the average of those two standard deviations, you wouldn't get the same value. They would be different. You can actually do this on your own if you like. So always make sure we're working with, starting with your variance estimates and then taking the square root of that to get your pooled standard deviation. Okay. So, I know, based on my confidence interval, that I'm already going to reject the null hypotheses, right? And I know, or I should suspect, that if I have evidence, sufficient evidence to reject the null hypotheses in 2 samples of 10, I must be working with a pretty big effect, right? I can look and I can see, well, that's a difference of 8. That seems to be, if we're thinking about these in terms of like 0 and 100 grades, a 93 is substantially different than an 85. We're talking about a low N and mid B, right? But if we actually calculate a standardized effect, right, I'm going through and saying, based on my hedges G, I'm saying the individuals who watched Sesame Street in high school are scoring an average of close to 1.8 standard deviations above individuals who didn't watch Sesame Street, right? If our benchmark for a large effect is 0.8, this is a massive effect here, right? What's my only concern with this estimate? What do you think, Nick? Just calculating G in and of itself.
Well, your samples are small.
My samples are small. So this is a massive effect, but maybe I sort of hang out and say, well, this is probably an overestimate because I'm using small samples. Maybe an unbiased G is going to be a better metric. So let's say G unbiased is going to be 1.789 times, I'm going to say 3 over 1 minus 4 times 10 plus 10 plus 2 minus 1, or excuse me, not minus 1, is that right?
Mm-hmm.
Yeah, okay. Oops. This is,
Isn't it 1
yeah,
minus?
there we go. 1 minus, there we go, that thing there. Yeah, I get 1.789 times 0.958. Is that what people got? Okay, which again give me 1.714. So here I would say, based on my calculation of unbiased G, I would say that these data is indicating that we would say, based on the sort of population estimate, we would say based on the data we've collected, we would expect population of high school students who formerly had watched Sesame Street in childhood will score about 1.7 standard deviations above the mean performance of high schoolers who were not exposed to educational programming in childhood. Okay.
That's a pretty big effect.
Yeah, that's a huge effect, right? And so for these data, if these data were real, oh yikes, man! You just like sit all kids in front of Sesame Street, man, and just let them go, right? This is obviously a contrived example, but again, that would be something that would be important to start thinking about in terms of, is Sesame Street good? Yeah, it's real good. Like it's very good, right? Now, problem is we can't rule out other types of things, right? Third variables, compounds that it might not be Sesame Street. It could be all sorts of socioeconomic types of things, right? But based on this, looks like there's something big going on here. Okay. All right. Finally, conduct a hypotheses test at alpha 0.05. Provide a comprehensive interpretation of your results. Really, the hypotheses test at this point is gratuitous, right? The only thing that we're really getting out of this is going to be a p-value. But if we want to go through and we want to do it, we would say, going to calculate a test statistic. Test statistic, our test t is going to be 8, right, which is mean 1 minus mean 2 divided by what? 2 is my standard error. Gives me a test statistic of 4. What was my critical value, Emilio?
It's been 2.101.
2.101, right? I've very clearly exceeded my critical value, and so I'm going to reject the null hypotheses. I already knew that because I calculated my confidence interval here. The only thing that we would do, perhaps, is go to
Want to get P value?
yeah. Find the one. Thanks, Bing, for not giving me the thing that I want. Okay, so here if we have a t-value of 4 with 18 degrees of freedom. Our p-value is 0.0008, right? So we would say associate this with p-value p less than 0.001 for a two-tailed test. Okay. And so then can sort of provide a comprehensive interpretation of results. Interpretation of results is going to bring in, and I would strongly encourage you to first, make an interpretation of your confidence interval, and then make an interpretation of your effect size, and then at the end you can say, sort of based on these data, we reject the null hypotheses, so that X is Y, and so then add in a p-value or something along those lines, right? Really, and this is why, again, methodologists will have pushed so strongly for the use of interval estimates as opposed to hypotheses tests, because we've said all we need to say pretty much by the time, and this is, I think, the frustrating thing on students' part is back, well, what do I say about the hypothesis test, right? You don't have to, all you have to tell me is whether you reject or fail to reject, right? Making sure you're telling me direction of effects, right? Just don't tell me, the one thing you don't want to do is just tell me that the people who watch Sesame Street and don't are different. Why am I not happy with that, Haley?
There's no direction.
I don't know, well, yeah, they could be different a lot of, well, not in a lot of ways, in 2 different ways, right? So one, to go through, talk about that, talk about your confidence interval for the point estimate of your difference, right? And then say sort of reject the null hypothesis p, sort of whatever, right at the end, and sort of wrap that up. I would prefer your attention to be focused on interpretation of your effect size, meaningful interpretation, or sort of meaningful interpretation of your confidence interval, your effect size. That pretty much wraps everything up, and then you just give me a p-value at the end, just because journals will want you to give you a p-value. Okay. Questions on this? Okay, cool. So this is doing everything by hand. But what happens if, and so we can go through and do this by hand fairly easily, right? We have a statistical program that'll do it, but we can do it by hand without too much difficulty. If we're savvy at programming in an Excel sheet, this can start to become really fast. But what happens though if we have evidence that's pretty good that our population variances aren't equal, right? Again, we're talking about a violation of our homogeneity of variance assumption. Let's say we get into the nuts and bolts of things and we find that, wow, actually it looks like our population, the variances of our population, our two populations of interest based on our sample statistics could be quite different, right? What do we do then, right? Again, the problem is if we violate this homogeneity of variance assumption, our test statistic that we're calculating over here, our t statistic, doesn't follow a t distribution. It follows a different distribution, right? But if I'm testing it on the t distribution that it should follow, then all of a sudden my probability values are off, which means my decisions on fail to reject are off, right? And I've run into some problems, okay? And so I've lost confidence in the accuracy of my test with this. A couple of different things that we've gone through and done. So there's what's called the Variance-Fisher approach, right? What Variance-Fisher did is they tabled T prime, so it's a T distribution for violations of homogeneity of variance assumptions, but it's just a limited number of distributions, right? It's not all possible degrees of freedom and all possible magnitudes of violations and things like that, so we're pretty limited here. So what we end up with is a Welch-Satterthwaite solution where we're interpreting T prime. So if we violated assumptions of homogeneity of variance, we're not working with T, we're working with T prime. And the distribution of T prime statistic isn't known, right? Welch-Satterthwaite solution is saying, well, T prime probably follows a T distribution, we just don't know which T distribution it is, right? So we're saying that the shape of the T prime, we probably have a distribution for it. We're just having trouble. We need to figure out which distribution it is, right? And so what we do then is estimate the degrees of freedom for violations of homogeneity of variance based on this variance and the sample size of each group, okay? Howell teaches you how to do this by hand. I had once or a couple semesters used to have people do this by hand, but it's a long and tedious process and decided that was not a good use of your time. So we're not going to have you do that anymore. We'll let you go through and do, we'll let the SPSS or STATA do that for you, okay? So when we go through and we take a look at the tests that are assuming unequal sample variances, this is the correction that we're using for this. Okay. And one of the ways we're going to go through and try and detect for our independent sample tests whether or not we have violations of homogeneity of variance is going to be our Levine's test. So what Levine's test is doing is basically Levine is going through and it's taking each score, replacing each score with a deviation from the sample mean, right? It can be an absolute value or squared value. So you're taking, for every person in group A and every person in group B, we're replacing their score with a deviation score, the difference from their sample mean, right? And then what we're going to do is we're going to conduct an independent sample t-test based on the mean deviation score, right? And if that difference in the deviation score is statistically greater than 0, we're going to say, well, there's evidence for a reliable difference in the variation. Because that deviation score is either a squared or an absolute difference, is going to be a measure of average of deviation from the mean, right? And if we have, if our two samples are reflecting populations that have equal variances, the variability of individual scores, the deviation scores across our two samples shouldn't have differences in the averages or absolute deviation. If it is, then we say we probably have evidence for differences in sample variance, and so then we would go through here, if we've got a significant Levene's test, we would go through and look at using a correction here. Okay, so for our Levene's test, what are we hoping for? Are we hoping for a statistically significant Levene's test or a non-significant Levene's test? What do you think, Laura?
Non-significant?
Mm-hmm. Absolutely, and why?
Because if it's non-significant, it means that there is homogeneity.
Exactly, right? So this is a test where we don't want a small p-value. We actually are hoping for something that looks fairly equal across these two things, right? So again, remember that anytime you're trying to interpret a significant test statistic, 9 times out of 10 it just means something's equal to 0 or not equal to 0. Here, we want it to be equal to 0 because that's going to suggest that we have equal, at least comparable variances across the represented populations. Okay. Questions to this point? Got real bright outside all of a sudden, right? It's just we've solved our homogeneity variance process, and sun's coming around, right? Okay. I think last thing we're going to talk about here before we get into SPSS stuff, what happens when we violate our assumptions, okay? Sometimes violation of assumptions are problematic and sometimes they're not, right? If we've got a violation of an assumption and it's not going to functionally impact our decision at the end of the day, we don't want to freak out about it and start doing a bunch of weird stuff that complicates our analyses, right? But what we need to do is go through and take it, be able to note, sort of, okay, I have these things that are potential violations. Is this something that's I need to address, or is this something that should be fine? Okay, so if we're talking about violations of homogeneity of variance, right? If we have violations of, if we have a violation of homogeneity of variance, if we have evidence that our two samples are coming from populations with different variances, we would say that our test is robust. If we say a test is robust, it means it's probably going to give us the right answer anyway. Our test is robust if we have relatively equal sample sizes, right? So if I have violations of homogeneity of variance, but my sample size is relatively equal, that violation of homogeneity of variance probably isn't going to be a big deal, right? I should note it, but I should probably say, well, this probably isn't going to do much to my test, right? We can also have evidence of non-normality in our observed scores, right? So if we have, let's say we run our screening and we see our observed scores are really non-normal, right? They're really skewed. They're ugly, right? Our t-tests, our means-based tests are still really robust to non-normality in our observed scores because one, we're assuming normality of our sampling distribution of means, right? Not the observed scores. So as long as we have a reasonable sample size and our distributions are similarly shaped, we're probably going to be okay, right? So if I've got cell sizes of 50 and I've got skew in my two groups, but that skew is both going in the same direction, I'm probably going to be okay, right? But if I run into a situation where I've got decent cell sizes, but the skew of one is extremely positive, the skew of the other is extremely negative, that's going to screw with my results. Okay. Situations where my test isn't robust. If my distributions if my data have different shape and unequal variance, that's a problem, okay? And this is going to be really problematic in samples where my skew is going in opposite directions. So I'm looking at my screening. I have different shape and unequal variance. I violated my homogeneity variance assumption, and my one test or my distribution, my one scores are normal and the other one are crazy skewed. This is going to be problematic, okay? If I have unequal variances and unequal sample sizes, this is going to be problematic, right? So if my larger sample has a larger variance, I'm going to have too conservative a test, right? And if we think about how these are calculated, this makes some sense because my larger sample is weighted more heavily in terms of calculating my pooled variance. And if my larger sample has a much larger variance than my smaller sample, my pooled variance is going to be real large, right? And if my pooled variance is large, what does that do to my standard error? Makes it large, right? And so I'm going to have too conservative a test. I'm going to fail to, I'm not going to reject the null hypotheses enough. Same thing, if my larger sample has the smaller variance, again, that's going to make my pooled variance small. All things being held equal, that's going to drive my standard error down. I'm going to have too liberal of a test, right? So again, if we have unequal variances and unequal sample sizes, or if we have violations of normality and small sample sizes, right? If I'm working with samples of 10, 15, and I've got obvious problems with my normality and my distributions, this starts to become problematic, right? I know that my assumption involves distribution of sample means, but even with samples smaller than 25, I'm starting to worry about sort of those distribution of my observed scores. So we're thinking about robustness, right? When do I have a problem? And so this starts to come into your screening, right? At the end, when you're sort of making your recommendation as a consultant to the people saying, should I move forward with this or not? This is the type of thing you're working for, right? Like, well, you've got, your data are horribly skewed, but you've got reasonable sample sizes, and it's all being skewed in the right direction. You don't have any like extreme outliers in either one of these things, so you're probably robust, you're probably okay, right? But if you have not large sample sizes, if you have sample sizes of 15, now all of a sudden you're going to start to have problems with your outcomes, right? So knowing, one, what's a problem, and then two, being able to anticipate the likely consequences of that, going to be important for interpreting your data, the data that other people put out there. Okay. Questions about this? All right. So we'll jump in, and so open up your t-test file in SPSS. So independent paired, or excuse, not interpersonal, not your paired sample. Your MBA t-test file. All right, so do that, and then pull out your independent sample t-test screening handout. This one. All right. So we've transitioned from a single sample test to a independent sample test. So we've got a few more things to go through and check. Our screening starts to become a little bit more involved than what it was previously. So the sheet we're looking for is independent sample T screening. Okay. So, first thing that we're going to do with this is, okay, so for these data, we've got, again, accident survivors who've been diagnosed with PTSD, right? But for this scenario, we're going to say that we're interested in seeing whether or not men and women with PTSD, accident-related PTSD, are different in terms of marital satisfaction and social desirability. Okay? So we've got a situation where we've got two outcomes. Marital satisfaction, social desirability, measured on what we're going to call a continuous scale. And we want to see whether or not we see differences in mean level of social desirability, marital satisfaction across men and women who have accident-related PTSD. Okay? So our variables, you look at your handout here, the scores of marital satisfaction range 2 to 158, a Marlowe Crown range 0 to 33. So, what we want to do before we start running these analyses, we want to go through and make sure that we don't have huge violations of our assumptions, right? So Emilio, what's the first thing, based on that screening handout I gave you, what's maybe the first thing I want to do?
We need to check for any missing data.
Check for missing data, right? And here, we've got a sample of 27. That's pretty easy. Do we have missing data? Yeah, because that score's gone right there, right? But this can start to become problematic when you've got larger data. You can't just necessarily eyeball it, okay? So I'm going to teach you a trick in SPSS to start seeing whether or not we have missing data anywhere. One, we could just go through and sort this, right? Again, left or right click on the variable name at the top and just hit sort ascending, right? And anything with missing values are going to come right up to the top. Okay. Another thing we can do is we can go analyze, or excuse me, transform, compute variable. And let's say, I'm going to say I want to compute check. I'm going to make that equal to Lock-Wallace total plus Marlowe Crown. I'm going to hit paste. This is going to pull up my syntax file, and you can see here we've got compute equals compute check equals Lock-Wallace plus MC. If I run that in SPSS, if I calculate a score as just the addition of two different variables, if I have a variable that if I have missing values on any one of the variables in that statement, the sum, it just won't, it'll turn up as a missing value. So when we start to get into like regression analyses where we've got a bunch of predictors, right? And we want to see not just are there missing values on individual scores or on individual variables, do we have, who do we have a complete set for? In SPSS, this is a nice way to go through and do that, because I can just say equals check or scrap or create some variable that's the addition of all my sort of variables of interest, and anything that is missing a value across any of those is going to come up empty on that, and then I can go through and say, okay, these are the cases I'm going to have to throw out because they're missing values and things. Okay. So, but in this case, it's easy, right? Because I see that I've got one case where we don't have Lock-Wallace or Marlowe Crown scores. So what I'm going to do is I'm going to go File, Save As, Scrap or something, right? Because what I'm going to do is I'm going to change this set. Go through, I'm going to highlight this, I'm going to right click and hit clear, and that's going to be gone. Okay. I need everybody to look me deep into the eyes right now. Okay. So, Layla, I need you to look into my, Kate, you too. Everybody look at me. I'm looking into all of your eyes simultaneously. Never, 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 never run analyses on your original data set. Never do this. Because what you're going to do is you're going to delete things, you're going to change things around, and then you're going to save it, and that shit is gone. Okay? Always create, when you've got your data set, save a working file, right? So say it's sort of dissertation set underscore working or something like that, and then work from that. Not only do that, then have some place where you've archived your main data set. So this is your original set, that it's somewhere else. Never work from your primary data set, because if that's the only set that you've got, and then you delete that case is gone forever. You can't get it back anymore, right? So always make sure that you're creating some sort of working set and working from that. It will save you great amounts of heartache, and maybe your research assistant's too big. Oh, hey, guess what? I deleted a bunch of cases. I don't know exactly which ones they were. Now we need to go through and re-enter a whole bunch of stuff. Okay. So what I've done here is I've saved a different data set, because I'm going to go through and change some things around. And what I'm going to do is, on sort of wherever I'm keeping track of stuff, I would want to say, okay, I've had one case that was missing. Go down through and make sure I mark what that case was, what values were missing from there. So when I'm putting together my screen, I could say case number X was missing values for Lock-Wallace and Marlowe Crown, and was deleted, leaving me a sample of 26 people. Okay, so always make sure that you're documenting this stuff. And I mean, you could document it in your syntax file if you want to, right? You'd say, again, anything with a asterisk is going to be a comment. You can say deleted case X given no score on LW total or MC, right? Something like that. You don't have to do it here, but do it somewhere so you know how to go back through it, so you know what you've gone through and done, okay? So, got a full set, and so what I'm gonna do now is I wanna go through and I wanna take a look at my distributions, right? But, can I just look at the distributions in my full sample? If I'm looking for distribution of scores and outliers and things like that? Can I just run it like we did with the single sample test? What do you think, Elena?
No, but I don't know why.
Yeah, you're right. Why can't we just run descriptives, skew kurtosis, z-scores for the full sample?
Because you have two different groups.
Because I've got two different groups. I don't actually have one sample. I have two samples, right? I have men and women, right? A score that might be an outlier for men might fall dead center in the distribution of women, right? And so I need to separate these groups out before I start running my stuff. Remember this, you always, anytime you're doing a group-based analysis where you've got more than one group, always gonna have to go through and separate things out. And so the way we do this in SPSS is we're gonna go to data, or excuse me, yeah, data, and go down to the bottom here where we see split file. And select split file, and then I'm going to choose, you can choose either compare groups or organize output by groups. I like organize output by groups. That sort of helps me, well, I guess what I say compare groups, organize, it doesn't matter here. With a small example, compare groups is fine. We'll do that because that's what I've done on the handout here. And then I'm going to say I'm going to compare groups by my grouping variable, okay? And so what this is going to do, then I'm going to hit OK. After I, oops, well here, let me go through, I'm going to paste that in so that I have it in my syntax file, okay? And so I use sort cases by gender, split file by gender. So I have, if you'll notice, I have all my men and all my women lined up in order here. What happens when I split my file? Anything that I do, any analysis I run moving forward is going to be run separately for men and run separately for women. Okay? Now, if I were to go through and I were to sort this in any way, that turns my file, my split file off. But as long as I don't go through and sort the data, it's going to separate things out across men and women. Okay? So I've gone through and I've split my file. But what I want to do now is I want to go through and I want to take a look at my distributions. So I'm going to go analyze, descriptives, just like we did previously. And I want to take a look at my Locke-Wallace and my Marlowe-Crown. I'm going to go to options. I'm going to request skew and kurtosis values. Hit continue. And then when I click this box that says save standardized values as variables. Nick, why am I doing this?
Because that's how you would look at each case on the whole distribution.
Yeah, this is going to calculate my z-scores. And this is incredibly important. I want to calculate my z-scores separately for each group, right? Because what it's going to do is it's going to take, calculate z-scores for men based on the mean of men and the standard deviation of men. And I'm just going to look at z-scores for women based on the mean and standard deviation of scores in the women specifically. Always make sure that we're separating these two things out from one another. I'm really done with this. Right? I was a nice person. I was like, okay, Zophys needed our computer lab in biosciences for something. From here on out, no, you guys can get that program in a different lab at a different time or something like that, because I would welcome you to come and try to do your stuff in here. All right, so go through, you're gonna go ahead and hit paste, right? And this should look familiar, right? This is the same stuff that we did previously with our independent sample tests, right? So what I'm gonna do is I'm gonna go through, I've split file already, but I'm gonna highlight my descriptives and I'm gonna run this. and here's what we get, okay? So someone help me out. Kate, tell me what I'm getting or seeing in these data here.
You're seeing data for females.
Okay, seeing some data for males and females separated. What types of things are standing out based on this output? From a screening standpoint, what might I take notice of?
I think there's a lot more detail than.
Okay, perfect, great. One of the things I'm going to key in is saying I've got 4 times as many women as I do men, right? I've got a hugely unbalanced design, right? And so that's going to be problematic, right? So in terms of screening, one, I'm working with small samples in both of them. But I'm working with small samples, exceptionally small samples, and Angela, you want to just go down there and check and make sure it's not someone just jerking around down there? 'Cause that happens sometimes.
That sounds too good to be honest.
Yeah, well, who knows? We got, I don't know, we were just hanging out on the other side, and some dude just like wanders by playing saxophone underneath I'm just, because I'm an undergrad, I'm just going to walk around campus and play saxophone. And he was stoned. But, so we've got small samples and unequal samples, so this starts to become problematic, right? I already know that my tests are not going to be super robust if I start to add in additional violations, right? Okay, so thank you, Kate. What else, Amanda, might I be looking at here in terms of thinking about my screening, my checklist stuff?
Standard errors are pretty big differences.
Okay. Well, standard error is going to be determined at least in part based on my scaling, right? My sample size, right? Sample size is equal, but this is kind of a factor, a scaling factor. What about my minimum and maximum? What might be important to take a look at there?
How much overlap there is, how big the range is.
Okay, so range, what might be an important thing to key in based on range if I'm going through and screening my data? Any idea, John?
I don't know about you, but I was just thinking like the scores are if you like graphing on however shifted more for the female, something like that.
Okay, so looking at some of that stuff. At a very basic level.
Help you find outliers?
What's that? Not the range necessarily, although maybe we might do it. What I'm going to be looking at my min and max to make sure my values are falling in the range of my scale, right? Like, are these reasonable values for the scale, right? So we see Lock-Wallace range from 2 to 158. Min max, that's good. Min max, that's good. Mahler-Crown 0 to 33, that's good. That's good. Perfect. Okay. Always want to make sure, because I don't want to have, say, a 0, because this happens, and I was going to call up our graduate students and say, hey, we've got these 0 to 10 rating scales. Someone's a max value of 100. We need to go through and fix that, right? Someone's just keyed in an extra 0, but always want to make sure that your values are sort of reasonable for whatever it is that you're measuring. Okay. Here, that's looking pretty good. Okay. So going through. We can start doing, sort of looking at average differences in scores across men and women here. But really what I'm going to focus on are maybe some skew and kurtosis values, right? So it looks like for men, I don't have really too much of a problem in terms of skew for the Lock-Wallace or the Marlowe-Crown here. But my kurtosis values are kind of large, right? Without looking at the distribution, if we think skew kurtosis less than or equal to about 2, so these are above 2, so negative kurtosis. Hey, what does negative kurtosis look like?
Does that mean it's not flat?
Yeah, kind of square and boxy, right? So it looks like we have problems with negative kurtosis there. So that's going to key something in. I want to keep an eye on that. For women, though, I've got, again, some evidence of negative skew, some evidence of negative kurtosis, but not too bad, right? So not anything I'm too worried about, at least at this point, okay? So I want to make a note to myself, so different sample sizes, that's going to be an issue, and then maybe some possible concerns maybe with the distribution in my min. should I be concerned with distribution in men in general, given everything I know up to this point? Why might I be more concerned about my observed distribution in my male sample? What do you think, Laura?
There's only 5.
'Cause I got 5 people, right? I can't have crazy distributions with only 5 people, right? That's going to make me more vulnerable to outliers, more vulnerable to a lot of problems, right? So I'm not super excited about where we're at this point, right? So what I'm going to do now is I'm going to go through, I want to get graphs looking at histograms for both of these. So I'm going to go to graphs, I'm going to go to chart builder. What's the situation down there?
There's a dance troupe. They're playing music.
Okay.
Loudly.
Is it?
It's a dance like class, like our instructor.
Okay. All right. I don't know, because it could be just a random, like,
It's
you're
like-
not a dance group,
No,
you're just a,
there's like 30 people on stage.
Okay.
This is
All
the
right.
real deal.
well, they're keeping it down for right now, I guess.
They're teaching them steps right now.
Oh, good. All right, so I've got, oh, whoops, not my bar, I want a histogram. Histogram, I'm gonna have my Lock-Wallace scores there. I'm gonna hit paste, and then I'll go graphs, chart builder, and this time I'm gonna put my Marlowe crown, drop that in there, and hit paste. Okay. So I haven't gone through and changed around, or I haven't sorted my data, so my my split file is still on. So what this is going to do, it's going to graph scores for men and women separately on both of these outcomes. So I'll highlight, run this, okay, and so here's my histogram for marital satisfaction for men and for women, okay? What am I seeing in my distribution for men, Layla?
We have, it doesn't look like a normal distribution. There are more extreme scores,
Yeah.
both on the lower end and upper end. We don't have too many people in the middle, but we do only have 5.
Yeah,
So-
and that's the thing, right? So it's hard to say much of anything. I mean, we can say we've got, it looks like a fairly square distribution, but we've got 2 people here and 2 people here and 1 person here. We can start to see where that negative kurtosis is coming from, right? We only got 5 people, right? We're not gonna get a nice, clean distribution with 5 people. We're gonna get garbage that looks like this, right? But I know why it looks like garbage, because we've got 5 scores, right? So that's gonna make me probably less concerned about sort of the negative kurtosis thing. That looks like it's a factor, in a matter of only having 5 observations here. If I go down and I take a look at my marital satisfaction scores among women, pretty straightforward. We have, again, we looked at our indices of skew and kurtosis. We didn't have too much of a problem here. Maybe I'm looking at this, looks reasonably, okay. Not terribly, there's nothing really super exciting going on. Maybe a little bit of evidence of negative skew going on here, in that sort of more distribution is falling outside, up, down on this end, but pretty straightforward. So nothing much going on that we'd be too concerned about here, right? If we go down through and we take a look at our social desirability scores, again, with our men, we've got 5, right? So we've got basically a square distribution here. Again, this is going to sort of map on. We can start to see where that skew of -2 something is coming in. And again, women about the same thing. Maybe some lean of a sort of slight negative skew going on. We can see that, but it's not anything huge or problematic that we get too worked up about. So we're feeling pretty good about that. Okay. Want to go through and maybe take a look at our box plots. So again, if we go back up to graphs, chart builder, and we go box plot, we pull that up there, and we'll start with Lock-Wallace, paste, Marlowe Crown, paste. So basically we've just put together syntax for our box plots here. Again, we're still on split file because we haven't sorted anything. If I go through and run that, again, getting my box plot for Marlowe Crown, or excuse me, my box plots for marital satisfaction. Men, we call this is just a symmetrical, box plot symmetrical. We're not worried about that, right? Women, box plots, again, fairly symmetrical. We see maybe a little bit evidence of sort of some of that negative skew. We got our median value here, a little bit more falling down on the distribution, but again, no values that appear to be problematic. Same thing with our social desirability. Looks pretty good, straightforward here. Nothing too terribly concerning with this. Okay. I have a confession to make. Realized this last night. So this is something that's been sort of itching on the back of me. But it really hit sort of when I started putting together sort of the Stata stuff and comparing output from Stata, output from SPSS on the box plots. There are more sort of values that are falling labeled as beyond 1.5 times the interquartile range in SPSS versus Stata. Trying to figure this out. Turns out sometimes Stata doesn't give you correct box plots, or excuse me, SPSS doesn't give you correct box plots. In the last, in this single sample test, your box plots, those values that are said that are supposed to be indicating 1.5 times the interquartile range above and beyond, like a couple of those aren't actually 1.5 times the interquartile range. I don't know exactly what's going on. SPSS seems to correct this issue if you're using reasonably large samples, but I don't know what's going on. So in general, sort of interpret these with caution, and if it's important, make sure, sort of, you may want to go through and, I'm not going to go through and double check, so I'm going to let you sort of, I'm not going to make you correct for SPSS, but know that for these box plots, sometimes values that fall outside the interquartile range, or 1.5 times the interquartile range, particularly if it's a small sample, they may not actually fall outside 1.5 times the interquartile range. You can actually calculate that yourself and say what value should and shouldn't fall below. So I don't know. I need to do more digging, figure out what SPSS is doing. It appears to not be a consistent issue, but at least in small samples it is. So just beware of that. Okay. All right. So based on our evaluation of our distributions, do we have too many concerns? No, right? So this is good. We at least don't have crazy outlying values. So what I'm going to do last is I'm going to go through and I'm going to go and ask for analyze, descriptives. I'm going to take a look at my z-scores. Okay. Drop those in. I don't need z-score my z-scores. That gets excessive. I don't need skewer kurtosis. Unclick those. I'm going to paste these in. And so down here, this is going to give me z-scores for my men and my women. Again, my split file is still on because I haven't changed any of that. I go through, run those. Am I seeing any problems with my z-scores here for men and women? What do you think, Kate? Yeah, am I seeing problems with my standardized scores in my male and my female samples?
I think I did it wrong here and I can't see that, so.
Okay. Anybody who's got this in front of them? Leila, any problem with standardized scores?
I'm just making sure, yeah. They're.
What do you think?
The range?
Yep, we're looking at the range, right?
Looking at the range, it's not that, oh, it is a lot. Yeah, it's going from -1.16 to 1.13.
But in terms of absolute values, do we have too many concerns with this? No, right? Looks pretty good, right? And it would be weird to find like a huge z-score either in the positive or negative direction at this point, right? Because we've gone through, we looked at distributions. If something was way out there, we probably would have saw it on the graph, right? But here, we're saying that our standardized, all our scores for men fall within plus or minus 1.26 standard deviations of the mean, right? For women, we see scores on both of these fall between sort of within 2 standard deviations, right? Absolute value plus or minus. And so again, we're not too concerned. This is all sort of seems reasonable, right? This is actually not the correct z-scores on your handout. Lump everybody together. It shouldn't. It should separate things out. Angeline, will you shoot me an email? Tell me to correct the handout. Basically, I don't have the split file on that, and that's just sort of lumping everybody together. This is a more effective way to take a look at this. Okay. So overall, so this kind of covers our bases. So at the end of the day, are we concerned about stuff? Well, we've got small samples and we've got really unequal samples, right? That's not good. But luckily, we don't have evidence of any outliers or unacceptable distributions, so we're feeling pretty good about ourselves up to this point, outside of the fact that we're going to have limited power and we'll have an unbalanced design. Okay. What's the last thing we didn't check with this? What's that?
Skewness and kurtosis.
Okay, so
Discuss that.
yep, we got skew and kurtosis at the very beginning. What's our assumption? What's our new assumption that we didn't test? Homogeneity of variance, right? We will test this when we actually run our t-tests. Okay, so we're doing good to this point. So go ahead and we're going to jump in and actually run our tests. This actually ends up being taking a fraction of the time of going through and doing all this stupid screening stuff. But before we run our t-tests, I'm going to go through and I'm going to go subject, right click, sort ascending. Why did I do that? Yeah, to turn my split file off, right? I can go through under the menu and turn it off, but if I try and run a t-test with this, it's going to return an error to me because it's going to try and run my t-test separately in men and women, and if men and women is the thing I'm trying to test it on, SPSS will give me an error with that. So I'm going to go through, resort that so that we turn that off. Now I'm going to go to Analyze, Descriptive Statistics, or excuse me, Analyze, Compare Means. Go Independent Sample t-test. I'm going to click this, okay? Now what I'm going to do is I'm going to say I want to look at differences in my marital satisfaction scores and social desirability, right? And my grouping variable is going to be going to compare this by gender, okay? Now it says, you'll see gender, question, it says define groups. I'm going to hit define groups. What's my code for men? What are men coded as? 1. And women? 2. Okay. This is nice. Let's say, Evelina, I have 3 conditions, right? So I have a condition variable that's coded 1, 2, 3. I can still run an independent sample t-test comparing 1 and 2, 1 and 3, and 2 and 3, just going through and telling it which conditions I want to go through and code. But in this case, we've just got the 2, so we'll go through and say 1 and 2. In general, if you're coding things like anything that's a dichotomous variable, I didn't do it here, but in general, we try and code things 0 and 1. It's going to make things easier when we get into regression types of stuff. It doesn't matter. You can code this 98 and 74 if you wanted to. I don't know why you would do that, but you could. But as we start to get into correlational types of designs, 0, 1 is going to be important to go through and code things there. So we're going to go through, hit continue, and then we've got everything put together. If I wanted to calculate a confidence intervals for stuff that was at a different level than 95, I could just go to options and put like a 99% confidence interval or whatever I wanted to, but we won't. We'll keep that standard. I'm going to hit paste, and here's my t-test. Okay? You go through and run this. And here's my output. Okay. Always want to go through, so we just spent a whole bunch of time looking at our screening, and so we already know what our means and standard deviations, so on and so forth, are about, right? But always want to look at your group statistics here first, just to make sure that you're testing what you think you're testing, right? We have men, women, for the Locke-Wallace, Marlowe-Crown. Here, I can go through and say, I can probably already guess, am I likely to find a difference in Marlowe-Crown social desirability scores? Probably not, right? They've got like a 0.2 difference going on here. Probably not going to get much out of this, but maybe a little more evidence for maybe something going on with my marital satisfaction. Got standard deviations and my standard error, right? Again, if I wanted to calculate a 95% confidence interval, Haley, around the point estimate for marital satisfaction in men with accident-related PTSD, could I do that from this?
Yes.
Yeah, pretty easy, right? I just say, here's my point estimate, here's my standard error, all I need is a test statistic for my critical value with 4 degrees of freedom. That's sort of gonna give me a massive confidence interval, but I could do that if I wanted to, right? So going through checking that to make sure that we've got what we think we are testing. And then here's our independent sample t-test, okay? So first thing, I'm gonna look at my Locke-Wallace score. First thing here we'll see is our Levine's test for equality of variance, all right? John, do I have problems, or are these data suggesting to me problems with homogeneity of variance?
No.
No, how do you know that?
Since it didn't come up significant, it's not suggesting there's like
Exactly, right? So my Levine's test, my F test for my Levine's is not significant. So these data aren't telling me I have huge problems with differences in the variances across these respective populations. So I'm pretty good. So because of that, what I'm going to do is I'm going to go through and interpret the test statistics in equal variances assumed. Okay? So if I go through and I look at this, here's my test statistic, my degrees of freedom, and my significance value. Amanda, what is this test telling me?
You have a very low significance.
Well, so I have a small p-value. So what does this tell me? It tells, am I going to reject a null hypothesis or fail to reject a null hypothesis?
You're going to fail to reject them.
Okay. Remember, we want if we're going to reject a null hypothesis, we want small p-values,
Oh, okay.
right? So our p-value here is 0.033, assuming that our alpha level is 0.05. This is a two-tailed test, so we would reject the null hypotheses that marital satisfaction in the population of men and women exposed with accident-related motor vehicle accident-related PTSD is equal, right? Evelina, specifically what's going on here, right? So telling me that they're different is not terribly informative. What, based on this statistical test, what does it look like is going on here? Look back up at your means. Who's reporting greater levels of marital satisfaction? Women, okay. What's that?
There's more of them.
Okay, there's more of them, but what we've gone through is we've gone through and calculated pooled variance estimate, and we've gone through and done that stuff. So even though our sample sizes are unequal, and that's kind of problematic, we've gone through and taken a look at and done our screening to say it's not optimal, but it's probably not going to be something that impacts our inferences all that much, right? So based on this, we would reject the null hypothesis and say it looks like there is, based on these data, a difference in marital satisfaction among accident survivors, among male and female accident survivors in terms of marital satisfaction. Here we've got a mean difference of 28.5 points, and then we've got 95% confidence interval around our point estimate of the mean difference in marital satisfaction across male and female accident survivors.
So
Okay.
that significance value just needs to not be 0?
No,
I mean, essentially.
Our p-value, we're looking for p-values less than 0.05 in terms of our up or down vote,
Okay.
right? So that's what we're looking for, right? And so we would say with a p equal to 0.033, we would reject the null hypotheses and say we have, based on these data, we have evidence for reliable difference in terms of mean average marital satisfaction across men and women. Okay. What about, though, Laura, if we drop down into, and we're looking at social desirability, okay? Do I have a problem with homogeneity of variance here?
Technically no, but it's pretty borderline.
Okay, I could hug you right now. Very good. Yes, technically this is over p less than 0.05, but it's not by much, right? Also, what do we know about the power of this Levine's test, or what should we assume about the power of the Levine's test based on everything we know about these data?
I mean, it's not going to be great because of the difference in the sample size.
Well, difference in the sample size, maybe, but more so the sample size itself, right? If I had samples of 200 and 300, right, and I found a significant Levine's test, should I get too worked up about that? Why not, Emilio?
Because they're very large sample
Because that's going to be a massively powerful test. It's going to detect differences that are probably trivial, right? What I might do then is go through and actually look at sort of the difference between my variance in sort of one group versus the other to see whether or not it's a big, actually, if I have sort of a lot of difference or something that's not really. Here, if I square this, I've got a sort of variance of 36 in my men and 16 in my women-ish, right? This is borderline, but I'd probably go through here and probably jump down and interpret equal variance is not assumed, right? Given everything else, right, the differences, the discrepancy of my samples and things, or the discrepancy of my sample sizes, I might be conservative and jump down here and interpret equal variance is not assumed, okay? And if I go through and do this, does it actually make a difference, Laura, in terms of which one of these I interpret? No, right? I mean, I've got a difference of less than 1/4 of a point, right? My p-value is 0.913 versus, it doesn't matter, right? Based on these data, right, how do I interpret this null effect based on these data? What do you think, Emilio?
How, like, in terms of hypothesis?
Yeah.
You would fail to reject due to inadequate evidence.
Fail to reject, okay, and that's what I'm looking for. So do we say there's no difference across men and women? No. We just say we don't have sufficient evidence to claim there's a difference here, right? And then what we might do is we might go through and calculate our effect size, and if that effect size is infinitely small, then we would say there's nothing going on here. In general, unless I tell you explicitly to do it, I don't need you to go calculating effect sizes for things that are clearly not significantly, statistically significant, but so that's how we might go through and approach this. And again, we have our point estimate of our mean difference, confidence interval for the difference in marital satisfaction across men and women. That difference, based on our sample data, could be anywhere from 8.5 points in one direction to 8 points in the opposite direction. It's a massive with 0 dead center in the middle, right? So based on these data, we really don't have much evidence to suggest that there's a meaningful or a reliable difference between these two groups. Okay. All right. What's the last thing we might want to do here? What do you think, Nick?
Effect size?
Effect size, yeah. Let's go through calculating effect size for this. And let's focus on the Locke-Wallace because that's what we have evidence of an effect for. All right. So what's the point estimate of our difference here? What do you got, Layla?
I didn't calculate.
Oh, you don't have to though. This is the beautiful thing about just sort of utilize what you have in your output, right? So what do we have under mean difference for our Locke-Wallace?
-28.
Yeah, 28.644. The negative's kind of arbitrary. I mean, if we flip it around, it's just sort of one versus the other. So we'll leave it at that. But what do we need to do in terms of getting our, and so for here, do we have a good comparison group? No, right? We don't have like a real good control, right? So glasses delta probably doesn't make sense. We'll go through and calculate a G statistic. But what I do need to do is calculate my pooled variance estimate, right? Because I've got problems with unequal sample size. So my pooled variance is going to be 5 minus 1 times, all right, what's my variance going to be for men? Olivia, do you have it? Yeah. So we'll just go through and put 30.366 squared. Okay, it's 121 point, okay, 921. Okay, we'll leave this so I don't have to have too much on there. But, and then we're going to go, all this is going to be behind the screen. 21 minus 1 times 24. This is stupid. Started too far in the right direction. Pooled variance, okay? I'm going to have essentially 4 times 30.366 squared plus 20 times 24.415 squared over 5 plus 21 minus 2. Okay. And if I run that out, I'm going to get a pooled variance of 650.426. And if I go and take the square root of that to get my pooled variance, or my pooled standard deviation, I'm going to get 25.503. So if I do go through, calculate that, then take my pooled variance estimate, plug it back into my effect size score here. So I've got 25.503. It's going to give me an effect size of 1.123. Okay. And so what I'm going to say, right, in terms of making my interpretation here, I would say, based on the data collected, we found a difference in marital satisfaction on the Lock-Wallace of 28.6 points, with men scoring lower marital satisfaction than women. Based on a 95% confidence interval from these data, we would expect the actual difference in the population of male and female accident survivors to range from anywhere from about 2.5 to 54.8 points, right? Is there data consistent with large effect with men scoring about a little over 1 standard deviation below women in terms of overall marital satisfaction? As we would reject the null hypotheses and conclude reliable differences in marital satisfaction across population of male and female accident survivors, sort of p less than, sort of p equals 0.003 or 0.033, something along those lines, right? So going through, tying all this stuff together, basing most of your interpretation on your confidence intervals and your effect sizes, and then rolling in sort of the test statistic stuff there. Okay. What's the only thing that I might want to do with this here? What do you think, Laura?
With what word?
So with my effect size, with my hedge is G, what might I want to, what's the one thing I might want to address here?
Difference in samples.
Okay, so difference in pooled estimate, pooled variance estimate kind of gets at that. What might I want to adjust? Yeah.
You're gonna want to adjust for the small sample size.
Yeah, I might want to correct this with an unbiased test, right? And if I go through, you can do that, it was unbiased G. I end up with 1.087, right? Doesn't make a huge difference, but it makes some. Right.
Static picking those out.
What's up?
Is static picking those out for you automatically?
Stata will,
Okay.
yes.
Okay,
SPSS will not,
okay.
but Stata will do this. But what I will do and what we will do is we will work on effect size calculators in Excel. So regardless of what you want to do or what program you want to use, you'll have that to be able to sort of automate some of these calculations. Okay? Questions? All right, cool. So we still have